All right, good evening. Welcome to the 12th and final Physics 1290 tutorials, at least final for problems and homework related help. There may be some future tutorials that we will plan to help out with preparations for the and studying for the final exam, but this is the last tutorial that will cover homework and lecture content. So tonight we have 4 questions to wrap up the unit on magnetics. So we have a question on torques that are experienced by loops carrying current in a magnetic field, and a couple topics on induced EMF, and lastly, the Biot Savart law as well. So let's dive right in. Question 1 should be on the screen. It says, consider a thin wire that has been tightly wound into a coil with 210 turns on a square frame, and the square has side length L. The wire carries a current of 1.02 amps, and it's placed in a magnetic field of about half a Tesla. So we're asked to find the angle that's formed by the area vector of the coil and the magnetic field if the torque of the coil is 1.5 Newton meters. And we're told that the coil kind of is free to rotate as it needs to. So one thing that sometimes people forget or find is a little challenging to perceive, if you have something that's like, say, a square prism like this one, the area vector with respect to this kind of square cross-sectional area is perpendicular. That's the key. So if you have something that is kind of like a planar area, this would be kind of the area vector here. So for this square loop, the area vector is in fact pointing more or less out of the page, or given the coordinate system we have, the area vector is kind of pointing along the x direction, or along I hat. And usually when you're dealing with topics of magnetism, oftentimes we choose the direction of the area vector to correspond to the direction of current flowing through the loop. So in this case, as we can see, current is flowing through the loop kind of like this, because we have this first arrow here. So it's circulating in a counterclockwise manner. So you can use a right-hand rule where you kind of curl your fingers in the direction the current's circulating, and your thumb points in the direction of, in this case, the area vector. So in our case, we can consider the area vector for this pointing out of the page. All this is good stuff to understand, but it's actually not necessary to complete the problem. This is kind of just, we have details here. And if we recognize what equation to use from kind of the lecture notes and what you've been taught, then it's pretty straightforward. So the torque is just equal to the number of loops times the current flowing through the circuit times the area of the loop times the magnetic field sine theta. So this would normally come about from a cross product. So we'd be taking the cross product of the area vector and the magnetic field. That's where this sine theta comes from. But we care about the angle in this case. That's what we're trying to solve for. So we can use this here, which is essentially the scalar form, which just solves for the magnitude. So we can rearrange this a bit. Sine theta is equal to the torque divided by NIAB, or simply that the angle is equal to the arc sine, or the inverse sine of the torque divided by NIAB. And it's as simple as that. I guess if we really want it to be thorough, the area explicitly for a square loop of side L, it's just NI L squared times the magnetic field. So that's it. I'll leave the calculator work up to you guys if you want to figure it out at home, but that is just the very straightforward answer to this question. So the second question here on the screen says we have an infinite wire carrying current I. It's been bent into this shape here, so there's a circular loop, but there's also a part that is kind of, it's sort of piecewise, but it's an infinite straight wire here. So you have an infinite line in a loop. We're asked to find capital R, which is the radius of the circle part, such that the magnetic field at the center of the circular loop is 0. So the way that this is set up, we kind of have a magnetic field from each piece, and we can treat these pieces independently. So what this is going to end up being is there's a magnetic field. We want to find out when that's 0. That's equal to the contributions from, I'm going to use the subscript W for the straight wire, W for wire, plus the contribution from the loop. So I'll give that B subscript L. So before we write in the values for those, we can figure out kind of what's going on graphically and just how this works and get a handle on what's happening. So if you have current flowing through, we can just pretend this wire is continuous and long. If you have current flowing to the right, there should be a magnetic field that's created. The direction of that magnetic field we can find. Let's maybe make a note on the right here for a wire. We can point our thumb in the same direction as the current. This again is always for right hand, not left hand, but this is the right hand rule. So you put the thumb on your right hand, you point in the direction of the current, so that'll be to the right as you're facing this. If you curl your fingers, that tells you the direction of the magnetic field. So specifically, the magnetic field kind of curls around and forms circular, it circulates around the wire. So the direction that it circulates is determined by the directions that your fingers curl. So you could imagine that if your finger is pointing, if your thumb is pointing to the right, then your fingers will kind of curl such that at the location of the center of the circle right here that we're looking at, the magnetic field is coming out of the page. So we can label this as B from the wire in red. We can same thing, but let's switch to red for the circular loop. In this case, we can curl the fingers in the direction that the current is going around the loop. And then our thumb will point in the same direction as the magnetic field. So with the fingers on your right hand, notice that the current is circulating clockwise here. To get your fingers doing kind of a clockwise orientation, you have to kind of invert your wrist. If you stick your thumb straight out at that point, it'll be pointing downwards into the page, or so you have something like this where at the center of the circle, the magnetic field is pointing downward. So we have a kind of or downward if you're looking down, this kind of into the page and out of the page, I guess, are better terminology. So you have a magnetic field contribution that's pointing inward and outward. If we gave this kind of 3 unit axes, we could have Z coming out of the page. So we have one of these that is along positive k hat and one of these that is along negative k hat. If they point in opposite directions, then if the magnitudes are correct, then they can add up to 0. And to figure out what the magnitudes are, this will be the first time we've used the Biot Savart law. So we switched to, well, I can show how we would switch to scalars. So we said that the wire contribution was coming out of the page. We'll say that's in the positive k hat direction. And the part from the loop was going into the page. That's minus k hat. And then the k hats, they can divide off because this is equal to 0. So what is the magnetic field due to an infinite straight wire? This is a result that hopefully was provided in lecture. This is just kind of solving the Biot Savart law for a particular geometry, kind of like with different charge distributions. You guys figured out what the electric field might be. This is just the same process, but it's given the name the Biot Savart law. Specifically for a wire, This is equal to mu naught. So this is like the magnetic analog of epsilon naught that we learned about when talking about electrostatics. So mu naught times the current divided by 2 pi times the perpendicular distance from the wire to the point of interest. So in this case, that is r, lowercase r. We picked up a minus sign, this k hat, and then we need to insert the result of the Biot Savart law when you solve it for a loop. So it looks pretty similar. Again, you have mu naught times the current. The presence of mu naught in the current is kind of like in electrostatics, the presence of epsilon naught and a charge, that kind of thing. In this case, we have 2 times the radius of the circle. At this point, we just want to solve for capital R. The mu naughts on both sides go away. And what we're left with is, as do the 2's, I guess, is 1 over R is equal to 1 over pi times little r, or the radius of the circle needs to be pi times r so that the magnetic field at the center was 0. So pretty straightforward result. If you guys can plug in the numbers here if you want to figure out an actual numeric value. Problem 3 is a similar, involves the Biot Savart law again. What we're told is there's a proton approaching an infinite wire with speed 100 meters per second as shown. The current in the wire is 5 amps. We're told to suppose that the proton is 1.5 meters from the wire. We're asked to figure out what is the force on the proton, and we're kind of just given some help orienting the unit system or the coordinate axes. I hat pointing to the left, J hat up, and K hat out of the page. So we have a moving charge in the vicinity of a current carrying wire. The current carrying wire, we know, is a magnetic field, and when a moving charge is in the presence of a magnetic field, it feels a force. So we know that, yes, let's first find out what the direction of the magnetic field is. Let's kind of just draw what's going on, and then we'll worry about the numbers after. So if we use the right-hand rule that we wrote down right here for a wire, we put our thumb in the direction of current. So that's pointing your thumb towards the bottom of the page. If you then curl your fingers, that tells you how the magnetic field circulates around the wire. So in this case, if your thumb is pointing downwards, when viewed from above, that's clockwise rotation, so it'll look something like this. So this is how the magnetic field will circulate around the wire. And if it hasn't really been drawn so well here, but if we say that at the tail end of this vector, that's where the proton is located. You can imagine you have to visualize this, the way the magnetic field is circulating in kind of like a 3D scenario, 2D page. But at this point, the magnetic field will be pointing into the page. In case that's not clear, we could also comment that on the right-hand side, it'll be pointing out of the page, and hopefully you can imagine how the vector field would look. So the magnetic field will point into the page. We know that the force on a moving charge in a magnetic field is just given by QV crossed with the magnetic field. So again, we have a right-hand rule to determine what the direction of the force is. That force is a vector, of course. So if you put your fingers in the direction of QV, which in our case points to the right, so your finger is pointing to the right. If you curl them in the direction of the magnetic field, so keeping your hand in the same position, but curling your fingers down, or keeping your palm, I guess, in the same position, curling your fingers down, you'll find your thumb points upwards, and in fact, that is the direction of the force. So now we've kind of figured out what direction this will be, and we can just boil this problem down to solving for the magnitude of the force. So the force is equal to QVB we should have a sine theta here, but we already know that V and B are perpendicular, so sine of 90 is just 1, so I'm going to ignore that. And we know that the magnetic field is the magnetic field from this wire. So we need to insert the result from the Biot Savart law, which is mu naught I over 2 pi times the distance at the point of interest from the wire. So I didn't label this, but we're told that the proton is d equals 1.5 meters. So that is this distance here. So magnetic field is mu naught I over 2 pi times lowercase d. And this is really our, I guess we know our charge is positive E. So our final answer is the electron charge, or the elementary charge, times V times mu naught times I divided by 2 pi d. And if we want to write this as a vector like we were told to, we know that this points upwards, and the details of the problem told us that we should take k hat as pointing out of the page. So we don't want that, we want j hat pointing up. So that is our final answer. And finally, the last problem here deals with Faraday's law and Lenz's law, which are typically applied simultaneously. So we're told we have a square loop of wire, side length L, and it's in the XY plane, centered about the origin in this region here with magnetic field. So we have some amount that you can see the vectors here where the x values are negative. So notice that x goes down to the left in the positive direction. So up and to the right, we have a positive field. The vectors point upwards. Where x is positive, the magnetic field points downwards. So we have this kind of, we made a plot of magnetic field as a function of x position. It would be something centered about 0, like this. And this right here would be x equals 0. So in case you're having time visualizing what this diagram is actually showing, hopefully this graph helps. Actually, I have this backwards, so hopefully I can correct it and then it helps. Looks like this. So it's positive when x is negative, the field is negative when x is positive. So the loop is moving. So we're given a velocity vector kind of at the back there. It moves at 6.43 meters per second in the negative x direction. We're told that this quantity W is 17.4 centimeters. So really what that means is that it's equal to L. And all this really means is that the region of magnetic field is sufficiently big that it fully encapsulates the loop. Like the loop would have to move by a distance of beyond L to get outside of this region. So for the purpose of our problem, we don't need to worry about the magnetic or the loop leaving the region of magnetic field. So we're actually told to do does it actually tell us in here what we're doing? Doesn't tell us. I guess that was an error transcribing the question. Let me just double check. Yeah, so we want to find out what the induced EMF is. And we want to figure out what direction it's going. So as the loop moves, moving towards the back of this plot, is moving in the negative x direction. The amount of magnetic field that is piercing through the area of this loop, otherwise known as the flux, initially is 0, right? There is this region here that I can carve out in blue. That has L, the area is L by L over 2. and that has a flux, which is the magnetic field multiplied by the area multiplied by the angle between the two, which is equal and opposite to this region at the back here. So those sum to 0. But as the loop moves, less and less negative magnetic field will be piercing through the loop and more positive magnetic field. So the flux through the loop will become increasingly positive. And if there's a changing magnetic field, or sorry, a changing flux through any closed loop, that will induce an EMF that will drive a current around the loop. The sign of that current will be determined by the magnetic field which it creates to kind of correct the action of the changing flux. So that all sounds pretty complicated. I think it'll be more clear if we do it, solve the problem, and it should become fairly straightforward as we go along. So let's kind of start over. The first thing we want to talk about is the magnetic flux. So the flux, broadly speaking, or generally speaking, is just the dot product of the magnetic field with the area. Or if we want to reduce this to just kind of things with only scalars, just be a cosine of theta. So it's the product basically of the magnetic field in the area, and the cosine theta is there to take care of any misalignment. Because our area vector points along the z-axis and our magnetic field points along the z-axis, we can conveniently ignore the cosine theta. So what we have in this case is we have kind of the magnetic field is pointing upwards, so I'm giving that a subscript positive, piercing through some amount of the area of the loop, which is positive, plus something similar for where the magnetic field is negative. So how are we going to figure out exactly? We want to write down an equation for these. I'm going to tidy this up just really quickly. So I'm going to call this point right here, or maybe this distance here to the point from the origin, I'm going to call that x. So in the region where the magnetic field is positive, we have a value of B for the magnetic field, and the area as a function of this coordinate x is equal to L minus x. So that's this distance here. And also the width of this region is also L. So that is the flux kind of in this positive region of magnetic field. In the region where the magnetic field is negative, we have minus B, not positive B, and the area is just equal to x times L. So hopefully that makes sense. Kind of the distance here I said was going to be x, and the width of it is L. So we can factor this just to make it a little bit more tidy. We have BL times L minus 2x. So all I did was I factored this L and this B, along with this L and this B, and everything that was left, I just combined it. So the amount of flux that we have as the loop moves is just determined by the equation we have here. Now the combination, more or less, of Faraday and Lenz's laws is that there's an induced EMF. The negative is really where Lenz's law comes into effect. Times the number of loops, or number of coils in the loop, times the time derivative of the flux. Or if you don't have kind of a function, if you just have, if you know the flux was, say, originally 10, and then it goes down to 0 in a certain amount of time, you could rewrite this as delta phi divided by delta t. But we're going to use the first form for now. So we only have one loop, so n is going to be 1, it'll go away. Trying to solve now is negative time derivative of BL minus BL times L minus 2x. So the time derivative of this whole thing. So B and L are just numbers. So those come outside the derivative. So what we have left after I did that operation is we have time derivative of L minus x. L is just a constant, so when you take the time derivative of this, it becomes 0. And finally, once we apply the time derivative to x, that's really all we have left. We have positive 2BL dx by dt. Conveniently, the rate of change of s is just going to be equal to the velocity. So our induced EMF is equal to 2BL times the velocity. So this is kind of how we find the numeric value. What we also want to do is we want to properly be able to assign the direction of the current flow, which will be pushed around by this EMF. So as the loop is moving backwards, the magnetic field going through the loop, or the amount of flux, is becoming more and more positive. That kind of makes sense. Eventually, you could imagine a situation where the loop is back here and the entire flux is positive. So as it moves backwards up until this point, it becomes more and more and more positive. There's more positive magnetic field going through the loop. So what Lenz's law says is that the induced EMF that comes about tries to correct any changes in flux going through the loop. So if the loop is moving backwards and kind of this applied magnetic field is becoming increasingly positive, then the current induced by this EMF, or the current due to this induced EMF, creates a magnetic field that points in the opposite direction. So there's a magnetic field that will point downwards because of the induced current. What direction does the current have to flow for the resulting magnetic field to point downwards? Well, we just use the right-hand rule, point our finger kind of following the direction of the magnetic field. The direction that our fingers will curl in that orientation tells us which way the current will go. So your thumb should point downwards, your wrist will kind of be turned upside down, and you'll find that your fingers will circulate in a clockwise direction. So the current will follow an induced EMF that is pointed like this. So we're going clockwise around the loop in the context of the question tells us when we view from above, if the induced EMF is clockwise, then we say it's positive. So that is it. That's all I have for you guys tonight. Hopefully this is useful in terms of wrapping up the final homework. And as I might have mentioned, or as I mentioned when we started out, stay tuned, watch for an announcement. We will have some sort of help session or tutorial session in advance of the final to kind of help you guys with your studying. I don't know if we will just do practice exam questions or some other questions, but we will figure it out.